Hi, so let's take a look. We're on day 3 of related rates, or day 4 depending on how we're doing this year. So let's talk about poor little Olaf. It's been a hot day in Arendelle, and Olaf has lost his little flurry cloud. As a former student of Mr. Warnell's, Princess Anna decides to do a little bit of calculus. And she determined that Olaf's bottom half, which is the shape of a sphere, is melting at a constant rate of 8 cubic inches per minute. So what do they have already given us? So Olaf is obviously melting, so he's losing water. But they give us this change in volume. So the first thing I'm going to write out is my change in volume. The change in volume, dV dt. And we're going to make it negative because he's losing water. He's melting. And that's going to be inches cubed per minute. And then they say the question, how fast is Olaf's bottom radius decreasing? So we want to find out how fast his radius is decreasing. So that is another rate, so we're asked to find the change in radius, or dr dt, when his volume is 100 pi cubic inches. So they give us the volume as 100 pi inches cubed right there. So to answer this question, of course, we're going to need an equation. The equation that we have is the volume of a sphere, which is 4/3 pi r cubed. And when we take the derivative, we're looking for the change in radius. So we know we're going to take the derivative. Remember, this is implicit. It's a related rate, which is implicit with the derivative with respect to time. So when we take the derivative of volume, we get dV dt equals, bring down the 3, and we get 4 pi r squared. Don't forget the derivative of r, which is dr dt. So we take a look at everything we need here. We have dV dt. We're looking for dr dt, but if you notice, we don't have r yet. So we have to find out his radius. So we have to find r. To do that, we're going to look at the equation. We know that the volume is 100 pi. So if I use my original equation, 100 pi, which is my volume, equals 4/3 pi r cubed. And so this is going to solve for radius for me. Of course, pi's cancel, and we're left with r cubed equaling, and this becomes 300 divided by 4, which is 75. So I'm going to use my calculator for this one, and you take the cube root of 75, and we get roughly 4.2172. Or if you want to leave it more accurate, the cube root of 75, that's okay as well. And now we can just plug our everything in. So we're going to get negative 8 equals 4 pi r squared. Excuse me. Whoops, I should go ahead and plug in my r there. So we get negative 8 equals 4 pi times 4.2172 dr dt. And when we solve for this, when we solve for dr dt, and again I'm going to use my calculator here, and I'm going to type that in, and you would get negative 0.0358, and the units, remember, radius is measured in inches, and time is measured in minutes. So it's inches per minute. So we can say that Olaf's bottom's radius is decreasing at a rate of, remember, it's decreasing, we already said that, so we keep this positive, 0.0358 inches per minute. And that would be our answer right there. Very easy to do. Alright, the next question asks, how fast is Olaf's surface area decreasing now? So now we're asked to find the change in surface area. So we can be fancy. The change in surface area with respect to time. And the equation for surface area of a sphere is 4 pi r squared. So when we take the derivative, we're looking for the change. The change in surface area with respect to time is 8, due to power rule, pi r to the first, and don't forget it is implicit, so we get dr dt right there. And when you plug everything in, the change in surface area with respect to time is 8 pi. My radius, which we already have in part 1, 4.2172. And my drdt, which we also found, was negative 0.0358. And if you type all of that in your calculator, you get this negative 3.794. And that's going to become inches squared because area is inches squared. And my change in time is in minutes. And as a sentence, we would say, Olaf's bottom's surface area is decreasing because it's negative. It's decreasing at a rate, again, we're saying it's decreasing, so we don't need to put the negative here, 3.794 inches squared per minute. And there we have poor Olaf. Hopefully we get him to an ice chamber or back to that Let It Go singer. Oh my gosh, look at him. Anyways, hope we get back. Hopefully Olaf will have a better day. Alright, so let's go to example number 2. So example number 2, this is like really kind of a cool question right here. This is how NASA used to track how fast rockets would go up in space for a long time ago. Before we had computers that could do all of this for us. So we have a hot air balloon. It's rising vertically and is tracked by an observer located 4 kilometers from the liftoff point. So let's take a look at what this looks like. Always draw a picture if you can. If you have a picture, it's good. So we have a hot air balloon rising up in the air. There's my hot air balloon. And an observer 4 kilometers away is watching this balloon rise. At a certain moment, the angle between the observer's line of sight and the horizon is pi over 5 radians. Remember, we always are going to be in radians here. So this is pi over 5 radians, this angle is. And let's see here. And it's changing at a rate. Oh, look, they give me this derivative. They say it's changing at a rate of 0.2 radians per minute. So I am now going to go ahead and list out my givens. I might as well. Well, the first thing they tell us is that the observer is 4 kilometers away. And they tell us that the angle, which is pi over 5 radians, and the change in radius, d theta dt, is 0.2 radians per minute. And they're asking us to find how fast the balloon is rising. So I'm going to go through here. Anything, remember, that does not change, that changes, gets a variable. Well, of course, the height of the balloon is going to change, so we'll just call that h. Will this distance down here ever change? No, this is a constant, so I'm not going to get a variable for that. But as the balloon is rising, this angle will change, so I'm just going to call that theta right there. And they're asking me to find the change in height, dh dt. So I need to come up with an equation, and because I'm using angles, we are going to get trig with this one. Okay, so we got to use a trig function on this one. So I want to use one that's going to involve my constant, and I might as well use my opposite side because that's h. So I am going to use tangent, and I know that the tangent of theta is equal to the opposite, which is h. Now that's a variable. This is changing, so I'm going to keep that as a variable over my adjacent side, which is constant. Remember, this is constant, so I'm just going to go ahead and leave that alone. And some people don't like h over 4, so we can rewrite that as 1 over 4h. Makes the derivative a little easier to take. Yeah, ready? And here we go. Let's go and take the derivative. We would get secant squared theta. Don't forget the chain rule. d theta dt equals 1/4 dh dt. What's really kind of neat about this one is if you notice in the equation here, does the height of the balloon really matter? No, to find the speed, the height doesn't matter because it goes away. So we need secant squared of theta. We already have the angle there. So we would get the secant squared of pi over 5 d theta dt, which is 0.2, equals 1/4 dh dt. And if we do this, dh dt would equal 4 times the secant squared of pi over, that's pi over 4, that should be pi over 5, sorry about that, pi over 5 times 0.2 And what we wind up with, now I typed all this in my calculator earlier, and you would get 1.222 kilometers per minute. That is a fast-moving balloon. I would probably jump off it really quickly. Hopefully I have a balloon, an air parachute. Psh. Psh. That's my parachute right there. You'll be safe. So we would say that the balloon is rising at a rate, because it's going up, it's positive, is rising at a rate of 1.222 kilometers per minute. And there we have it. This is a good question to know. Now, sometimes students always say, Mr. Warnow, could I have used any trig function for this one? Absolutely you can. Let's imagine we chose sine of theta. Instead, we would get h over, this would become like r, that would be changing, r. But if you notice, because neither one of these are constants, the derivative becomes a lot tougher. So we would get the cosine of theta, d theta dt equals, but here we would have to use quotient rule, which would become low derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. And that's a lot harder to deal with because, one, we don't know what r is and we don't know what dr is. Dr dt is. We'd have to calculate those. And that's a lot harder problem to do, which is why I would suggest always use one of your givens, what you're trying to find, and a constant if you can. Makes these a lot easier to do. Okay, so go into part 2, we'll finish up these notes here.